So now we're going to look at using the reference triangles that can be drawn for any angle to evaluate functions like sine of 45 degrees. So here are a couple terms that you will hear often in this class. First, what is a reference triangle? Well, reference triangles are the triangles that can be drawn by looking at the terminal side of your angle, wherever your angle is specified. If you draw a straight up or down vertical line from there and connect it to the x-axis, that'll be perpendicular to the x-axis. And then you can go from there back to the origin or the center of the circle to create a triangle. And then the sides of that triangle can be used for evaluating trig functions with your SOHCAHTOA rules. Quadrantal angles, this is another term you will often hear. These are the ones that land on either the x or the y axis. So it's the ones at like 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360. And it goes on forever and ever if you just keep adding 90 at a time. Or in radian mode, you could do that as well. So you would have 0 radians, pi over 2, pi, 3 pi over 2, 2 pi, etc. Here we have a few examples where I'm going to show you the process of drawing a reference triangle, but I'm going to flip to a copy of the unit circle to show you this on that document for reference. So that first example had sine of 3 pi over 4. So I need you to know where the 3 pi over 4 angle is pointing, and you can see that that's the one that goes along this diagonal line. So I'm going to draw the line going along the 3 pi over 4 angle. And then if I draw a straight up and down line from 3 pi over 4, the terminal side of 3 pi over 4, and then connect it back over to the origin, we end up with a right triangle, because this vertical and horizontal line makes a right angle. And what I need to notice is that since 3 pi over 4, that covers almost all the way across, that leaves pi over 4 in here, or if you're doing that in degree terms, you can see that for the degree measurements, that's 135 degrees on this side. So inside of the angle, from the diagonal line the rest of the way down to the horizontal line, that leaves this piece being 45 degrees. So this is the important part of drawing our reference triangle. And then what I would do from here is know that the sides of the 45, 45, 90, we have 1 for the hypotenuse, and then we have root 2 over 2 for both legs. So since this question said what is sine of 3 pi over 4, now I would say, well, the rule for sine is opposite over hypotenuse. So sine of 3 pi over 4 would equal square root of 2 over 2 divided by 1, but do be careful about the signs, because like this is actually going to the left, so my x value would be a negative root 2 over 2, but since this one's going up, it's a positive root 2 over 2, and the hypotenuse is always positive. It's always a positive 1. So in this case, I get my answer of being square root of 2 over 2. So that was our first example, sine of 3 pi over 4. We drew a triangle based on where this angle was located, and then using the rules for opposite over hypotenuse to get this answer. Now we need to look at cosine of negative pi over 3. One quick reminder about negative angles: instead of on your unit circle starting from the right and going around counterclockwise, negative angles start from the right and go clockwise. So what I'm going to be doing is looking at going down pi over 3. The alternative way you could do this is you could add 2 pi to this angle, because this one's too small, and find the coterminal angle that it's the same as. Either way would be fine. So for cosine of negative pi over 3, like I said, I need to know that that means I'm going clockwise a length of pi over 3. So if I started here, this would be pi over 6, pi over 4, pi over 3. So my terminal side is going to be pointing in this direction, and then I go straight up and down until I hit the x-axis, and then I go straight over until I hit the center of the circle again. So again, the horizontal and the vertical pieces, that makes a right angle, and then I need to figure out what angle I have inside of the triangle. And so again, if you're pretty good with using the unit circle, these big gaps are 30-degree gaps, so that's 30, and then the small gaps are 15-degree gaps. So 30 plus 15 is 45. Plus 15 more is 60. So this angle ends up being a 60-degree angle, or you could have looked at that by saying, I know all the way around is 360, and I ended up pointing down at 300 degrees, so the difference between 360 and 300 is 60. As long as you can get that angle, that's fine. So that's our central angle, which leaves 30 degrees for the other angle over here. So So again, these special right triangles, the unit circle is always a radius of 1, which means my hypotenuse is 1. And the short leg across from 30 degrees has to be 1/2 of that. And the long leg across from the 60 degrees is going to be the short leg times root 3. So square root of 3 over 2. So now I have my reference triangle drawn, and the rule for cosine is to say the adjacent side divided by the hypotenuse. So in this case, be careful about your signs again. Since I'm going to the right, it's a positive x value, but for the up and down purposes, you might actually want to think of this as a negative square root of 3 over 2. So my adjacent side is 1/2, my hypotenuse is 1. If I do 1/2 divided by 1, that answer is just 1/2. And then one more quick example, we have tangent of 405 degrees. Now again, I can use the coterminal concept we looked at in the last section to make this a little easier to work with, because this angle is outside of the 0 to 360 range. So if I subtract 360 from this, then I would have 45 degrees. So instead of doing tangent of 405, I can actually do tangent of 45, and it'll be the same answer. So looking at my unit circle again, this time the angle I'm dealing with is 45 degrees. So my terminal side going across will be diagonally along this line. And then I'm going to go straight up or down until I hit the x-axis, and then straight over to connect it back to the center. So here's the right angle in my triangle for the horizontal and vertical part meeting. And since this was a 45-degree angle, that means I have 45 in this corner and in this other corner over here. The sides for the 45, 45, 90, we have 1 for the hypotenuse, and root 2 over 2 is the rule for both of the legs. And in this case, since I'm in the first quadrant, both of those numbers will be positive. It's going right, so positive x, and up, so positive y. Now the rule for tangent of this angle, since I'm doing tangent of 45, don't forget that the rule for tangent is opposite over adjacent. So I'm going to be doing square root of 2 over 2 divided by square root of 2 over 2. Well, a number divided by itself, root 2 over 2 over root 2 over 2, is just equal to 1. So that's my last answer. So there are lots of ways of evaluating different trig functions, but drawing a reference triangle, as long as you know where the angle is that they're specifying, it's actually one of the faster, easier ways to kind of do this, even mentally, once you've practiced it a good bit. Now let's look at some of the ones that you can't really draw a triangle out of. Those are the ones that we call the quadrantal angles. They don't make a triangle because they either go straight to the left and right, or they go straight up and down on the unit circle. They're on the x-axis or they're on the y-axis. So first, recognize that this angle is too big. This is not between 0 and 360. It's way too big, in fact. So what I'm going to do is subtract 360 from this angle to find a coterminal angle. Because if I take sine, cosine, and tangent of the new one I get, it'll give me the same answers. So 900 minus 360 will give you 540. Well, this is still too big. I'm still not at a number between 0 and 360. I'm still bigger than that. So I'm going to repeat the process. I'm going to subtract 360 again. This time I got 180 degrees. So hopefully you guys are starting to get familiar with where these angles are on the unit circle. So just as a quick rough sketch, for your unit circle, 180 degrees is pointing straight to the left. So I can't really draw a triangle out of this because there's no line to connect up and down and hit the x-axis with. So instead, I just need to think about my coordinate, which in this case is -1, 0. That's the ordered pair for the point I have at the end of the unit circle. So this is my x value and this is my y value, and I need to use the rules based on the x and the y coordinates for figuring out these three values. Now, since I can't draw a triangle, what we need to rely on instead is that sine of theta is going to be based on the y variable, cosine will be based on the x variable, and tangent will be based on y divided by x. So when I'm going through and listing my answers, sine of 900 degrees will be the y coordinate for my endpoint. So in this case, 0. Cosine of 900 degrees will be equal to the x coordinate my x-coordinate was -1. And tangent will be equal to y divided by x. So if you take the y-coordinate, 0, and divide by -1, 0 divided by anything is still 0. So most of your answers are going to be zeros and ones when you're dealing with the numbers on the quadrantal angle. And you'll just want to keep in mind that it's basically using the same SOHCAHTOA rules we were going over before, but since we don't have triangles, you just want to know that sine is the y-coordinate, cosine is the x-coordinate, and tangent is y divided by x. Here's another one where I'm going to be drawing a reference triangle, but I have to combine two facts here. First, I have to consider where is cosine going to give me a negative answer, because I want to draw a triangle, but the problem is in my x and y axis, my 4 different quadrants here, cosine is negative in 2 of them. So it could be this quadrant, or it could be this quadrant. So right now, I don't know if I want to make my triangle go up and to the left, or if I want to make my triangle go down and to the left, because cosine is negative in both of these. But if I also look at this cotangent rule that they gave me, we talked about the signs for sine, tangent, and cotangent. Well, cotangent is less than 0, which means negative, in this quadrant and this quadrant. So the one that meets both conditions, for it to be negative for both cosine and cotangent, that means it has to be in this quadrant too. So that's the first thing you should do when you're given one of these questions where they give you one fraction and then one where they just say the other function is positive or negative. Think about where the functions are positive and negative, and then see where they both match that information to identify which quadrant your triangle's in. Well, now that I have a triangle in the second quadrant, I can say, all right, that means my triangle must be going up and to the left for the terminal side. It has to be a triangle going up and to the left for my unit circle. My right angle would be down here. And then I can go back to this fraction here to say, all right, cosine is -2/3. Well, the rule for cosine is adjacent over hypotenuse. So from my central angle, theta, my adjacent side is the one here along the bottom of the triangle. That must be the negative because it's going to the left. From my origin, going to the left makes a negative x value. And your hypotenuse should always actually end up coming out positive. The only place where you'll have negatives are on the x or the y values, and that'll be based on which quadrant you ended up in. So anything in the second quadrant will have a negative x value, but a positive y value, and the hypotenuse will always be positive. So now that I have 2 of the sides of my triangle, I can use the Pythagorean Theorem to find the last side. So -2 squared plus y squared is equal to 3 squared. Well, -2 squared is 4, and 3 squared is 9. If I subtract 4 from both sides, I would have 5, and then take the square root. So I'm going to get the square root of 5 for this side. Now when they asked me to find sine and tangent, I don't know what theta actually is. This could be 20 degrees, it could be 50 degrees, I have no idea. But I do have the information I need to fill out sine and tangent because I know sine is opposite over hypotenuse. So since I have the 3 sides of my triangle, I can just write the fraction square root of 5 divided by 3. And I can do the same thing for tangent. Again, I have no idea what that angle measurement is, but the rule for tangent is opposite over adjacent. So I can write negative square root of 5 divided by 2. I just pulled the negative from the bottom out front of the fraction. You can really put it wherever, but usually we don't leave negatives in the bottom of a fraction. So either out front or on top is better. So drawing a reference triangle, even without knowing the angle, is possible as long as you use the rules for the signs of the 2 functions they gave you, and then Pythagorean theorem to find the third missing side. So here's a short word problem to describe the concept of a coterminal angle. If you've seen the Zoolander movie, the main character has this problem where he doesn't know how to turn to the left. He only knows how to turn to his right-hand side, which would be clockwise. But the unit circle is described as turning counterclockwise. So the problem is, if he is currently facing to the right at the starting position, he needs to end up facing this way, but he is not able to turn to his left 90 degrees. So what we need to describe instead is how far would he go to his right to end up facing in the same direction. So he would start from this position and then go clockwise 90, 180, 270, and then he would be facing straight north. He would be in that 90-degree position, but he had gone negative 270 degrees. So don't forget that positive angles measure how far you spin counterclockwise, negative angles measure how far you spin counterclockwise. So this is just showing you that a 90-degree angle in this direction is the same as a negative 270-degree angle. So it's very important to be able to convert between those two things. This is the same idea as finding coterminal angles, because if we want 90 degrees, you can either add or subtract 360, and that would give you another angle facing in the same direction. So I was doing the concept of subtracting 360, which concept-wise is saying spinning around one whole way, one complete revolution, but going in the opposite direction, in the clockwise direction. So that's where that negative 270-degree answer comes from. So instead of doing a quarter turn to the left, he has to do 3/4 turn to the right, and that's how we describe negative 270 degrees. And that's it for the notes. Thanks, guys.